Okay, guys, right. Learning curves. I actually enjoy this topic because I think it's one of those where you can be creative and you can sort of see what's going on. And it's a pretty cool. The idea itself, by our friend here, Mr. Wright, who we'll talk about, is a bit. Again, it's really kind of you see something very scientifically, a scientific way of observing, if you like, events, and then turning it, if you like, into mathematics, which I guess is really the point here. So let's see what we're saying here. So what we can see here is that it says we kind of see what's going on here. This is probably the first breakaway. Maybe this is the first jump, if you like, conceptually, in variable cost thinking, variable cost behavior, because we've always argued the variable costs are the same as you go along, right? They're always the same. With every extra unit, your variable cost is the same. There is no change. Variable costs. We're sort of breaking that rule now and saying that it's been observed that in some industries there's a tendency for labor time per unit to reduce in time. I mean, that makes sense, right? As more units are produced, workers become more familiar with the task and it gets quicker. So economies of scale. This is almost like a breaking down of economies of scale to a certain extent, the theory behind it in general, but this time to do with labor. Aircraft production during World War II reveals that the rate of improvement was so regular that it could be reduced to a formula, and the labor hours required could be predicted with a high degree of accuracy from this idea of from a learning curve. So your people are learning as you're going along, and they're getting a better understanding of what is going on. So, of course, the first time a new operation is performed, of course, both the workers and the operating procedures are untried. So it'll take them a long time to actually understand what's going on. But of course, as you do this, of course, as the operation is repeated, the workers become more familiar with the work, and labor efficiency, of course, increases, and the labor cost per unit declines. So key point is you've made the first unit, it's taking you an hour. We've observed that when you make the second unit, it will take you less time. The question here is, can we find a pattern, if you like, or a structure to that timing, and then therefore predict, if you like, or forecast what cost would be for a certain number of units. And that's really the goal here. Now, this is what's critical. This is the point. If you get this, you've got it. It says here that as the cumulative output doubles, so for example, when I go from 1 to 2 to 4 to 8 to 16 to 32 to 64, blah, 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 the cumulative average time, so my focus, guys, is on the average time, not on the total time. I can come back and look at the total time and make adjustments when I say adjustments and see what's going on, or even the individual time, but the cumulative average time falls by a fixed percentage. So what you always want, it says again, I'll repeat that, as cumulative output doubles, so this is as this doubles, the average time, I'm telling you that the average time, I don't know, doesn't really matter. I don't want to do it here on this slide, but I'm telling you that the cumulative average time, so I can have total time here if you want, but I'm not talking about total. My point is that this law or this observation applies to what's going on the average, and then I can come back and work out total, nothing tricky. Falls per unit falls to a fixed percentage of the previous. So it falls to a fixed percentage. You're going to get a percentage, or you could probably work it out as you see over time, a fixed percentage of the previous average time. And so what I think you kind of have fun with is that mathematics of sometimes you're given the average time here, you're given the average time, you need to work out what the percentage change is. And that in itself isn't tricky, but that's what's sort of, as I say, interesting about this. You can sort of play with the thing, but as long as you conceptually understand what it is you're looking for and where you're going, then you're all right. And what we're really saying is, as we produce more and more units, that average time we observe falls because you are getting better at making it, right? So if you make one unit, it takes you 10 hours. If you make a second unit, it takes you 8. Well, overall, the average time will fall, right? I mean, the total time falls, but when I say so, the actual time in itself falls to make the second unit, but we know that the average time falls, and we can actually find a pattern of that fall. We see that extra, you're making the units, and they're falling. I mean, we'll talk about what happens here. You can see that after a certain time, though, which we get questions like that, when you get to a certain point, the average time is just really the same. It's the same. Nothing's changing after that, and you should be comfortable to be able to get here and then kind of work out what's happening with the additional units, and there's no more change after a certain point. So it's reached I guess the technical term is a steady state. If you like, post a, I'm just going to call this X. Right, so for example, a 90% learning curve means, right, that each time cumulative output doubles, the cumulative average time per unit falls to 90% of the previous value. I've said always create a table. Again, it doesn't matter what figures I use. I could be as random as possible. What I'm saying here, I'll keep it simple. I'll probably see a table similar. If I make the first unit and it takes me 10 minutes to make the first unit. So I guess the total time right now is 10 minutes and the average time, right? Well, yeah, I don't want to have two curves. So I'll just call this if that's the total time to make the first unit, and therefore the average time, of course, will be 10 minutes, right? 10 divided by 1 is 10. What it's saying is that when I make the second unit, we have observed that the average, cumulative average, so is 90% of the previous time, the previous cumulative average. So therefore, the average time to make 2 units is 90% of the previous sort of event. And therefore, 90% of 10 is 9 minutes. So I'm telling you that the average time to make 2 units is 9 minutes, which means, therefore, that the total time to make 2 units is 18 minutes. Now, here's the thing. This is what I was saying where it's interesting. You can kind of start deducing from yourself by yourself thinking, that means if it took 10 minutes to make the first unit, well, it must have taken 8 minutes to make the second unit. So you had something that looks like 10 and 8. So the time it took to make the second unit was 8 minutes to make the first unit. And of course, the average, 18 divided by 2 is equal to 9. That's what we're getting at here. But it's cumulative. So I can't do 3 from here. No, I can only do 4. And I know that 90% of 9, again, is 8.1 minutes. So I know that the average time to make 4 units is 8.1, and therefore the total time is 8.1 times 4, which is equal to 32.4. So the total time to make 4 units is 32.4 minutes, and the average time is 8.1 minutes. And I can keep going, right? Of course, if I'm making 8 units, again, 90% of 8.1. 90% times 8.1 is 7.29. And this is so you will get questions that are just straightforward, like what's the time it takes to what's the total time it takes to make 4 units? Just kind of straightforward 1, 2, 4, 8, 16, 18, 32, 64 type thing. I'll come back to the other scenarios when I need to find out what's going on with 3. But in this first video, I just want to look at this kind of the natural progression here of what we can observe here. Okay, right. So, and of course, total time, of course, is increasing. Of course, you can see that. This is total time. It's increasing. If you like, you can see that curve there, 10, and it's increasing. But of course, that as well will start to hit some kind of steady state at some point. Right, so the learning curve, of course, has limitations. Typically, learning curves, as you can imagine, it must be to do with you making sort of the same thing where you're getting better. If you're making totally distinct products every single time, well, you won't see that kind of steady structure of learning curve. It's because you're repeating. So first of all, the process is typically labor intensive. Modern manufacturing is very capital intensive. So really, it's really if we can allow labor just gain that experience, really, isn't it? We're really talking about human beings here, but if you have machines kind of affecting that, then we have a product. I talked earlier about new products. The product new products make it more probable that there will be a learning effect. So we're working with the product and getting better and better. So we're repeating. It's really about repeat. If it's complex, though, of course, again, like I say, it's the truth is it's really about repetition. If we're allowed to repeat making the same product, then we see a learning curve. Of course, we will see some fatigue, if you like, over time. So people start getting tired, and then we start. So really, which is why I guess cost curves always look like this. Really the point is that at some point costs start to go up just because people are getting tired and we're seeing waste and that sort of thing. Again, key point here is, again, like I see the question really, but it must be about repetition, so that I guess, which is where, and we could bring it into economics, where I guess economics really argues about a different type of employment, a type of unemployment where once people who are in a job, once that industry ends, and you're trying to move them into another industry, or if you have a recession and you have people lose their jobs, you really want to try and keep them on, because the loss of certain skills are very difficult to reacquire because of all the gains that have been made as a result of the learning curve. And well, just-in-time products have moved towards multi-skilled and multitasked workers. So in these type of environments, because people are doing several things at once, sometimes you might lose the benefit of the learning curve. You can't quite observe it. Typically, it's very much it was designed around the repetition of the making of one product. This is exactly what I've just done here, where you saw that I had the time to make 1 unit, and the total time was 10, and the cumulative was 10. You can see this is a 90%. You can almost read it sometimes, right? You can see this is a 90. So if you ever get a question asking you about the actual learning curve rate, you need to be focused on the row with the cumulative average. That's the point. So you need to get what that cumulative average is, and then kind of see it, right? That must be 90% of that, and that's 9. And so the total time must be 18, and therefore the individual time must be 8. And you can sort of see, again, that's 90% of that, and the total time, of course, must be this. Oh, sorry, this is an observation. So they observed this and they collected these figures. So forgive me. So there's no way you can't find the 3 from our argument. You can only go 0, 2, 4, 8. But we're going to come back and see how we can find the 3. But this is the observation that they noticed. So you can see what I was doing here earlier on, where I'm now going to do 8.1 times 4. And I think 8.1 times 4 is equal to 32. 32.4. If I go back and see what they had 32.4 as well, right? You see, so an observation. And I could keep going ultimately. I can't know this because, again, I can only know the time it took to make the 2 units, but I can't even know this from here. And then, of course, I'll have 90% again times 8.1, and that's 7.29. And so the total time times 8 units is 58.32. And I can find all this. I can constantly keep finding this. 0.9 times 7.29 is 6.51. 561 times 16, and then we have here 104.976. And so that's the kind of picture we're building. Okay, great stuff. Yeah, and I think I'll end the video there, and then I'll now move into what happens when we're trying to find those kind of the 3 and the 5 and the 6 and the 7, if you like. Oh, basically we're looking at the curve and sort of saying, because on the curve we can then find what those individuals are. We sort of need to understand what the equation is, but that in itself isn't tricky. It's just applying the equation and working with the formula involved. Okay, great stuff. See you in the next video.